Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. In this video, we talk about a very important topic in neural networks and deep learning, which is called backpropagation. You have probably watched other YouTube videos or trying to go through some textbooks to learn about backpropagation, and I know they all seem very complicated. And one reason for that is that some of these resources, they assume that you have knowledge of calculus 2 and calculus 3. Therefore, I made this video to show that you can understand backpropagation with basic knowledge of calculus. And by basic, I mean that just by knowing derivative. What is the derivative of f of x equals x squared? It's 2 times x. So if you know this means that you can learn backpropagation today. And if you're not subscribed to the Dr. Data Science team, please consider joining the team. And I appreciate your comments and feedback. So let's get started. A simple neural network model looks like this. So we have the first layer, which is always the input layer. And then we have usually one or more hidden layers. So that's our hidden layer. That's where the magic happens, in the sense that we get the raw input data and we take these through some hidden layers before providing the output values. And here in this simple case, I have only one hidden layer, and this is the output layer. So in some cases, you might have more than one output variable. Let's say you want to both figure out if there is a cat in an image, and also you want to see if there is a dog. So each of these, they need to have one output variable in the last layer. So that's the general format. And when we have the weights for these connections that you see here, it's very easy to find the output, right? You take the inputs and you have this propagation through the network until you get the output. But the key idea is that we have to be able to find appropriate values for these weights, and that's when we have to use optimization techniques, and that's where backpropagation becomes important. So for now, let's say we want to solve this problem, and because this might look a little bit complicated, I just simplify this to convey you the main message behind backpropagation. So what I did here to simplify this, I assume that in each layer, I only have one neuron, right? So I have one neuron in the hidden layer, the blue one, and one neuron in the output layer. And also here we have the only like one input variable. You can extend this idea when you have more than one neuron, but then that's the point that you have to use a lot of indexing and things get complicated. So if you're trying to understand backpropagation, in my opinion, the best way is to consider the case that you have one neuron per layer. But even before we are going to use this simplified model, I want to tell you a little bit about partial derivatives and gradients, because that's something that we need and something that you may not already know. So why we need to use partial derivative? So as we said, when you have a function f of x equals x squared, you know that the derivative of this function with respect to x is equal to 2 times x. And remember, derivative is something that tells us about the rate of change, right? So it means that if x changes, how this function f of x will change. However, in many cases, we might have a function that has more than one variable, right? So here we have x1 and x2. So let's say this function is x1 squared plus x2 squared, right? So obviously this is a valid function. We have two variables, x1 and x2, and this is the form that we have. So now, if I want to find the rate of change, you may say that whether I have to change x1 and x2, and that's where we have to use partial derivative. So let's say I want to find the partial derivative with respect to x1. And by the way, this is a notation that we use for partial derivatives. So we are not going to use d as we did before. We use this partial notation. So that's the notation we use for partial derivative. So what this means is that when we want to find the partial derivative with respect to x1, we assume, that's the key word here, that x2 is constant. So that's the assumption that we make. So if x2 is constant, let's say it's 1 or 2, any number that you want to pick, any constant value, then what happens is that I get here x1 squared, and I know that the derivative of x1 squared with respect to x1 is 2 times x1. And then I have the partial derivative of x2 squared with respect to x1. But remember, x2 is constant. And what's the derivative of constant? It's 0, because constant doesn't change. So that means that the partial derivative is equals to 2 times x1. Now I can do a similar thing for partial derivative with respect to x2. And similar to before, I assume that the other variable, which here is x1, is constant. So now I have to find the partial derivative of x1 squared with respect to x2, and x1 is constant, so it doesn't change, so that's 0, plus partial derivative of x2 squared with respect to x2, which gives me 2 times x2. So in general, you may have a function with more than 2 variables. You may have like 10 or hundreds of variables. And the key thing here is that now I can define something called the gradient. So that's the gradient, which is an array that includes all these partial derivatives. So it means that here, the gradient has 2 elements because I have 2 partial derivatives. And the first element is 2x1 as we calculated, and the second one is 2x2. I can factor these 2, so I get 2x1, x2. And what this basically means is that if I have this function f, which has 2 variables, and I want to find the rate of change, I have to find the rate of change with respect to each variable separately. And these are the values. So with respect to x1 is 2 times x1, and with respect to x2 is 2 times x2, right? And that's something that we can see from here too, right? Because we know that if I have just any type of like quadratic form, x squared, the rate of change is 2 times x. And so now I have this f of x1 and x2, which has this form of x1 squared plus x2 squared. So this means that with respect to x1, rate of change is 2 times x1, and with respect to x2 is 2 times x2. So now you may want to wonder why even we care about gradient. The reason is that in order to find the weights of those connections in neural networks, we have to use optimization methods. And the most commonly used optimization method is gradient descent and its variance. So what does gradient descent does is that we are going to have some estimates. So in general, let's say I have some estimate of the solution, and then I'm going to move opposite direction of the gradient, and that's what gives me the new update. So this is your current estimate. This is the gradient, and alpha is just a positive constant. And the intuition is that, let's say if I have a function that looks like this, I obviously here use only one variable to just make it simpler to visualize this. But if I am here and I want to figure out whether I should go to right or left to decrease the value of this function, I have to go to the opposite side of the derivative or gradient when you have more than one variable. So this means that I have to go this side. So that's why I have like this negative sign here. And that's the general idea behind gradient descent that we use for optimizing the weights of neural networks. So I'm going to make another video to discuss more about this gradient descent part. I know that here I just talked about that very briefly, but my idea here is that to show you that why we care about the gradient and partial derivatives. Okay, so with this in motivation in mind, we have one more step to go back to that simplified neural network model that we have. So if you remember, that neural network had a lot of neurons in it, right? So it is important to understand how these neurons work. So the way that they work is that it's a little bit confusing because we are not showing the full picture. So the way that this works is that this neuron has two parts, a summation part, and then what we call as activation function. So let's say we have 3 inputs to this neuron, and here I just call them x1, x2, x3. Usually neurons in the middle layers or intermediate layers, they don't get inputs from the raw data, but they get from the previous layers. But for now, let's just assume that these are the inputs, and let's say these are the weights, W1, W2, W3. So this first part, which is here, computes something that we call it Z here, which is W1 times X1, W2 times X2, and W3 times X3. We can also use a summation notation so that we can see why I use that notation there. So that's Wixi, I equals 1, 2, 3. If you feel more comfortable with linear algebra, you can also create two vectors W and X, and then find the inner product between these two vectors. So that's how this last line looks like. So we have two vectors, and now we find the inner product between these two. And then the other part of this neuron, the second part, is that we're going to apply these activation functions. That's the way we show it using A. And now we have this function, which I show here with phi, and then phi of Z. So that's something important to remember here. So Z is what we have here, and A is what this neuron produces, which is simply phi of Z. I could obviously put these together and say that A is equals phi of W1 X1 plus W2 X2 plus W3 X3, but I don't want to do that because that will simplify things in the next slide when I'm talking about backpropagation. So having this in mind, let's go now to the model that we had before. That, as we said, we have one neuron per layer. So in order to name these, I call this X, right? I call this W1. So W1 is the weight that goes from the input layer to the hidden layer. And then I call this weight W2, right? So this is W1, this is W2. And the output of this neuron is A2, because here, let me use a different color. I use like a red color here to show that. So here we have A1, and here we have A2. And I don't really show here Z because Z is basically inside these neurons that we had in the previous slide. One way I can do this, actually, to make this simpler is to, again, show what we had in the previous slide, the sigma notation and the function that we have. So here we can see that we have, I showed here, Z1, which is W1X, and Z2, which is W2 times A1. And that's the point that I made in the previous slide, that for this red neuron, if you look at it, this gave the input to this is from the previous neuron, which outputs A1. So we multiply A1 by W2, that's what we give us Z2. And then we know that A2 is equals to phi of Z2, and A1 is phi of Z1. So I tried to make this as simple as possible. We have two weights, W1 and W2. And then we have these outputs A1 and A2. And the rest is basically using these simple linear equations. So the other thing that happens, because most neural network models are used in supervised learning. So this A2 is what the neural network produces. And we have also a target value, which is Y. So this is the actual output value that we like to see, right? And we usually compare these two things, right? Compare using some cost function. Let's call it C. Then in this case, I assume a simple function. We just use sort of like a mean square type error. We just subtract A2 by Y and we take this to the power of 2, right? So that's exactly what happens in the mean square error for regression problems. So now, in order to update these weights like W1 and W2, we need to use partial derivatives because obviously we have more than one variable. And also, we need to be able to find these partial derivatives of the cost function with respect to these weights, right? So the first thing that we want to do here is to find the partial derivative of C with respect to W2, right? This weight that goes to the output layer. So obviously that's a complicated problem. So in order to simplify this, we use something called chain rule. And it is very easy to use. In the way that you can think about it is that I always like to create this, what is called computation graph, right? So we have this A2 and we have Y, and these two, they give us C because C is equals to A2 minus Y to the power of 2. And A2 is given by Z2, and Z2 is given by W2 and A1. So just have this in mind. So now if I want to find the partial derivative of C with respect to W2, I can find the partial derivative of C with respect to A2, partial derivative of A2 with respect to Z2, and Z2 with respect to W2. So this is the path that we took here, right? So we started from here, then we went here, right? Then here, and then we went here. So we found all these partial derivatives. So now let's look at this. So what's the partial derivative of C with respect to A2? So this is a quadratic again term, right? So what you can do is that you can call these, let's say anything you want. I call this like B. What's the derivative of B squared? A2 times B. And remember, B is equals to A2 minus Y. And now you have to take the derivative of the inside these parentheses, B with respect to A2, which is 1, because derivative of X with respect to X is 1. And then now the second part here is what's the derivative of A2 with respect to Z2? So now we can use this equation here for that. So that's just simply the derivative of this function, phi, calculated at the point Z2. And then for the last one, we use this equation that we have here, that the partial derivative of Z2 with respect to W2 is equals to A1. So why this happened? So again, that's the part that we have this partial derivative that we have to consider. So I want to find the partial derivative of this term with respect to A1. Sorry, with respect to W2, that was the problem, right? So we want to find the partial derivative with respect to W2. So we assume A1, which is the other variable, is constant, right? And we know that if I have like 2 times X, what's the derivative with respect to X is 2, right? It's the constant that is next to X. So here, if I want to find the partial derivative of Z2 with respect to W2, we need to pick this constant that is next to it, which is A1. So I can just copy this now. And go to the next slide, right? So that's like what I found previously, that the partial derivative of C with respect to W2 is equals to multiplication of these three terms. And let me also again draw that computation graph that we have. So that's a good practice. So if you remember, we said that we have A2, we have Y, right? So we had the cost function, which was A2 minus Y to the power of 2. A2 is related to Z2, and Z2, if you remember, is connected to W2 and A1. Right? So now let's look at partial derivative of C with respect to A1. So in this case, I get partial derivative of C with respect to A2. I go step by step. A2 with respect to Z2, and Z2 with respect to A1. And here's where the magic happens. If you look at it, we already calculated 2 out of 3 terms that we have here. So this means that now I don't have to just start from scratch. I can just use these results that I have for both cases. And the only thing that is extra here that I have to calculate is this term, right? And let's remember, what was Z2? If you remember from the previous slide, Z2 is equals to W2A1. And now we have to again use the partial derivative. So we want to find the partial derivative of Z2 with respect to A1. So this means that we assume W2 is constant. And when we have a constant times a variable, the derivative is that constant. So this means that this partial derivative is W2. So now we have the partial derivative with respect to A1. And we can continue this process to find all these partial derivatives. How? So if you look at it, A1 is connected to Z1, and Z1 is connected to W1 and X, right? So let's look at it to make sure that we did this correctly. So if you look at it, Z1 is equals to W1X, where W1 is the weight, X is the input. So that's what we have here. Z1 is coming from W1 and X. And then Z1 goes through this activation function, gives us A1. And that's what we have here. So this means that now, if I want to find the partial derivative of C with respect to W1, we have already taken all the way this path up to this point. And that's like, these are the only extra steps that we have to take. And this is extremely useful because when you have a complicated model, then you will save a lot of computation by reusing these partial derivatives. So that's why I call this recycling. And as a practice, you can continue doing this with having more hidden layers because now it's easy. You don't have to worry about indexing because we have only one way to go from one layer to another layer. So if you look at here, W1 goes from the input layer to the first hidden layer, then we have W2, and now you can have W3, W4, and more. So this is the basic idea behind backpropagation, and I want to keep this video short so you can practice on your own and appreciate that how simple is backpropagation. I hope you enjoyed this video, and please feel free to like and subscribe.